Good afternoon, everyone. Welcome to my session. My name is Peng Gao Yan. Today, my presentation topic is integration of vehicle dynamic model and system identified model for navigation in autonomous mobile robots. I will present my work in following parts. Firstly, I will give a brief introduction to show the motivation and basic idea of this work, followed by which I will show the overall architecture of the proposed method. Next, I will introduce the two means adopted in this work, that is, vehicle dynamic model and system identification. Short background will be provided, and the integration of the two steps will then be illustrated. Then we design a numerical experiment to show the positioning and navigation performance of the proposed method. In the end, I will conclude the presentation and show the future work. Page number is given in the right bottom in case of your need. As we know, navigation is important in various applications. In autonomous mobile robots, such as autonomous vehicles, underwater robots, the importance of navigation is over loadouts. In these navigation architectures, motion model is the basis, which tells the robot the basic rule of movement, and the vehicle dynamic model is a kind of well-adopted motion model. According to definition in SAE, vehicle dynamic model is the application of the physical laws to a vehicle in motion, and its function is to provide course pose estimation. We can see that so many typical navigation systems adopt the vehicle dynamic model. For example, MU VDM integrated system in the UAVs and LiDAR VDM localization in autonomous vehicles. So is there any ways to improve the navigation performance instead of purely use the VDM? Well, usually we have two common ways. One is to introduce high precision sensors, another is to integrate multiple sensors. However, these improvements are done by introducing sensors. So anything can be done by utilizing endogenous information. We found that one possibility is to re-examine VDM. Firstly, let's take a look at the problems in VDM. Usually, there are two problems of VDM. One is that VDM makes assumptions about the environment. For example, like low speed condition assumption will assume that there will be constant road friction coefficient. Secondly, the VDM usually simplifies the system complexity. For example, it will overlook the latency caused by the control system. So, can we improve VDM? Well, definitely we could develop more complicated VDMs, which also means more parameters to be determined. So that means it will be hard to be used in practice. So is there any other ways which is suitable for all kinds of VDM? Well, in this work, we explore one possibility, that is, by introducing system identification. According to a definition given by Professor Yong in 2010, system identification is building mathematics models of dynamic system from observed input and output data. So how can system identification to correct VDM? Well, as we know, there are two factors of VDM estimated errors. One is unknown system characteristics, and another is the changing environments. And these factors have impacts on system responses. So system identification can estimate system responses in a data-driven approach. So there will be a correction. That is, we can use system identification to provide a better control input singular with the estimated response than the raw control commands. So the basic idea of this work is to use system identification to improve the positioning performance of VDM. Now I'm able to introduce the overall architecture of this work. The autonomous vehicle is taken as the experimental platform. In general, the autonomous vehicle usually consists of following modules. The localization module receives information from sensors to produce the localization results. Then the planning and control module will utilize it to generate control commands, and the commands will be executed by plans, such as engine. Here, we introduce the system identification. It will identify the system property by utilizing the control command and the measured responses. Its output will be the estimated response. Then VDM will take such estimated response as control command to make the pose estimation. The pose estimation made by such VDM can be used to develop an advanced positioning algorithm with the aid of sensors. In this work, we focus more on how system identification can correct VDM. Firstly, let's see some basic knowledge about the VDM. In this work, we adopted the kinematic bicycle model as the VDM. Figure 2 shows the basic idea of such model. In this setting, it uses two wheels to represent the four-wheel vehicle. Point A is the front wheel center, and point B is the rear wheel center, and the line between A and B is the wheelbase. Point C is the center of gravity, which divides the wheelbase into two parts, the LF and LR. It assumes that the rear steering angle is 0 and the front steering angle is delta F, and the intersection of the line perpendicular to the rear wheel axis and the front wheel axis is the point O, and the direction perpendicular to the line OC is the velocity direction, and the angle between the velocity and the wheelbase is the slip angle. And the x, y, and the phi of the point C defines the planar motion of the vehicle. Phi is the rotation of the vehicle. And in this setting, it assumes that the slip angles at both wheels are 0. Here, the slip angle means the angle made by the velocity and the wheel center with the wheel's orientation. And second assumption is that the vehicle must operate it in low speed. The differential equations of the kinematic model is given below. We can say x, y, phi's differential is related to velocity and the slip angle, and the differential of velocity is related to the acceleration, and the slip angle is related to the steering angle of the front wheel. So here, the acceleration and the steering angle is taken as a control input. We're now going to show how the VDM can be improved by system identification. Firstly, let's take a quick review. System identification is building mathematical models of dynamic systems from observed input-output data. In system identification, there are mainly three steps. Firstly, we need to collect input-output data, and then we need to select candidate models which can represent the relationship between the input-output data. Then we need to estimate the parameters of these candidate models. Now, we will focus more on the candidate model selection. In candidate model selection, there are usually two methods. One is the gray box modeling, another is black box modeling. In gray box modeling, we need to specify the model structure and then to estimate the unknown parameters by minimizing difference between model output and the measured output. In black box modeling, we only need to specify the order of transfer function or the numbers of poles or zeros. So this is a trial and error process. For simplicity, we use this method in our study. Now I want to talk a little more about black box modeling. In general, there are two ways to represent the system. In time domain, we usually use the function of time to represent the system. By taking the Laplace transform, we can get the representation of system in frequency domain. In here, we usually use the transfer function to represent the system. Here is the transfer function with n poles and m zeros. So in black box modeling, we can obtain models by specifying different numbers of poles and zeros, and then we can get a model G1, G2, G3, and etc. Then what we need to do is to get the best of those models. So what's the criteria to get the best model? Well, here are at least two common criteria for comparing the model performance. One is the fit ratio, another is the mean square error. In fit ratio, the essence is the normalized mean square error, and the bigger the better. For the mean square error, it's the amount of error in estimation, so the smaller the better. Now it's time to show how we do the system identification. In this work, the autonomous vehicles are taken as an example of autonomous mobile robots. The autonomous vehicle is simulated by the gazebo, which is a well-known simulator in the robot field. In such setting, we need to identify two subsystems. One is the powertrain system, another is steering system. The powertrain system converts the engine's power into movement of the vehicle. In gazebo, the control command of it is the velocity command. For the steering system, it turns the vehicle around the vertical axis while driving, and its command is the steering angle command. Now, I will firstly show how to identify the powertrain system. In identifying the powertrain system, the input command is the velocity command, and the output is the measured velocity. Firstly, we need to collect the data. In the first step, we fix the steering angle to 0, and then we design waypoints to make autonomous vehicles give a series of unit step velocity commands. The waypoints are a series of points with coordinates and certain speed. And the figure in the right shows the velocity command, and the amplitude is 1 meters per second. In the third step, we measure the system velocity by sensors such as LiDAR, and in the fourth step, we store command and measure the velocity. Then we need to select the candidate models. Here, we use the black box modeling method based on transfer function. We denote the candidate model as pxzy. P is the pole, z is the 0, and x is the number of poles, y is the number of zeros. So we can say we got 20 candidates, which is listed in the table. Then we just need to estimate the parameters of these models according to the input-output data. Here, we simply use the least square optimization, which is commonly used in SI. To focus more on how system identification will benefit the VDM, we omit the presenting of computational process in parameter estimation, which could be done by many software, such as MATLAB. Here, we just give a quick result. In this figure, we show the fit ratio and the mean square error of these candidate models. We can see the fit ratio of P5Z4 is around 0.893, and which is relatively very high. However, it also has very high order, which means complexity. When we look at the P2Z2, we can see it balances the model order and performance. According to research by Professor Yong, no order model is preferable in industrial practice. So finally, we choose the P2Z2, which has a low order with competitive performance. Next, we are going to identify the steering system. In identifying steering system, the input is steering angle command, and output is the measured steering angle. In data collection, firstly, we fix the velocity to 1 meters per second, and then we design waypoints to make autonomous vehicle give unit step steering command, and its amplitude is 0.52 rad, which is around 30 degrees. Then we measure the system angular velocity by sensors and convert it into steering angle. In the first step, we store the command and obtain the steering angle. And similarly, we choose 20 candidate models as that in identifying powertrain system. We can see in this figure, we can see that P5Z5 has the best performance but high order, and P2Z2 also balances the model order and the performance. So we finally choose the P2Z2 as the model of steering system. We must note that the parameter of P2Z2 here is different from that in powertrain system. What they seem is the model structure. Now we have already identified two subsystems. Then I'm going to show how to use such knowledge to improve the positioning performance of VDM. Here is the differential equations of conventional VDM. The figure shows the conventional VDM process. We can see the VDM directly takes the control command from the planning and control module. In our method, The control command will be sent to the system identification, and then the system identification will give the estimated response to the VDM, and VDM take this as the control command. So here, we replace the original acceleration with the corrected acceleration, and the original steering angle with the corrected steering angle. And then we name this as the VDM-SI. To demonstrate the strength of the VDM-SI, we design a numerical experiment. Firstly, let's take a quick look at the setting of the experimental platform. In this experiment, we use Gazebo as a simulator and use Altware to develop the autonomous vehicles. In the autonomous vehicles, the perception and the localization module is developed by the entity matching algorithm based on LiDAR, and the planning module is based on the pure pursuit algorithm. A control module is based on the incremental geometry. In the experiment, we design two scenarios. One is the 90-degree bend with a radius of curvature equal to 20 meters. Another is the S-curve with a radius of curvature equal to 50 meters. And the white dashed line is the design track. Firstly, let's examine the positioning performance of the conventional VDM and the proposed VDM-SI. Here is the experimental design. In first step, we start vehicle in constant velocity, and then we use LiDAR for navigation. In third step, we use VDM or VDSI for pose estimation in a separate program. Here, the separate program means that the pose estimation of VDM or VDM-SI is not used for navigation, but just for comparison. In fourth step, if the vehicle arrives at the endpoint, we stop the vehicle. We calculate the absolute translation error of VDM and VDM-SI in the two scenarios, and summarize the related statistic in the table below. In the 90-degree bend, the mean ATE of VDM is above 8, and the value of VDM-SI is around 2. The reduction of mean ATE is about 70%. And other statistics, including max ATE and RMSE ATE, shows the consistent improvement. And similar results is also found in the S-curve scenario. You can see the improvement in the two scenarios is around 17% to 80%. We can get a sense that the integration of system identification can improve the positioning performance of VDM. Secondly, we investigate navigation ability of pure VDM and VDM-SI without sensors. The phrase "without sensors" means that no sensors will be used to navigate the vehicle. Excluding sensors makes it more clear to understand the navigation ability of VDM and VDM-SI. This is also an important assumption, since there will be time when sensors are out of work, and we have to use VDM for navigation for a short time. Here is our experimental design. In the first step, we start vehicle in constant velocity. In the second step, we isolate all sensors from the vehicle at start point, but measure the vehicle state in a separate program. Here, the separate program means that this measurement will not be used in navigation. This can help us to check how much the navigation of the VDM deviates from the true state. Then, in third step, we use VDM or VDSI for navigation. In the fourth step, after the vehicle arrives at the location near the end point, we start the vehicle. We plot the translation error of VDM and VDM-SI in the two scenarios, that is, the difference between the estimated pose by VDM or VDM-SI and the measured pose by sensors in the separated program. In the left figure, we can see the translation error of VDM-SI is consistently slower than that of VDM, although all of these errors are increased with time. And in the right figure, you can see although the shape of error curve is different from the one in the left figure, the result is similar. We can say the VDM-SI has a much lower translation error than VDM. So in both scenarios, the translation error of VDM-SI is smaller than that of VDM in the navigation task. So we can say VDM-SI has a higher ability for navigation than VDM. In this work, we integrate system identification into VDM for navigation. The experiment showed the improved positioning performance and navigation ability. Another thing is that the loosely coupled structure of VDM makes it easy to be integrated into the mainstream sensor fusion-based navigation architecture. Our contribution are twofold. One, we build the relationship between system identification in the control field and pose estimation in the navigation field. The second contribution is that our research suggests the research direction in investigating the endogenous connection of the navigation system. Instead of looking hard into sensor fusion as in literature, we hope more research could be done in understanding the system itself. Nevertheless, this work has certain limitations and also suggests a possible improvement direction. Firstly, our work adopts offline system identification, but it's not suitable for time-varying system. Future work can consider use online system identification to capture accurate system dynamics. Actually, we are currently working on this direction. Hopefully, we'll achieve better performance. Secondly, to make the main ideas flow, we keep work settings simple and easy to be implemented. We only use LiDAR for measurement. However, LiDAR cannot measure the acceleration. Therefore, we only identify the velocity response of the powertrain system instead of the acceleration response. So future work can use other sensors, such as MU, for directly measuring the acceleration in identifying the powertrain system. Thirdly, our work mainly focuses on improving the positioning performance of VDM by integrating system identification. Future work can integrate VDMSI and sensors to further improve the positioning performance, such as LiDAR and camera. Here is a list of references used in this presentation. Thanks so much for your attention, and I'll be very happy to answer your questions. If you are interested in my work, you can also contact me by email.